Hello, everyone. Thank you for attending this session. I know it's not easy to come after a heavy lunch. This presentation going to have a different perspective, which is focusing on the improvement that we made in the lab to widen the application of sustainable concrete, specifically fly ash-based geopolymer concrete in the field. So my name is Lateef Assi. I'm the Material Department Manager with the Terracon consultants. So the outline, first of all, I will talk a briefly overview about the sustainable concrete, specifically fly ash-based geopolymer concrete. And then I will talk about the case number one is improvement. How did we improve the early and final compressive strength? And the second one, how did we eliminate the need for external heat? The third one, I will talk about the effect of the fly ash source and particle size distribution on the compressive strength. And the fourth one, I'm going to talk about the controlling the initial and final setting time. And because we have just four presenters, I will talk verbally about fifth case study, which is the real world application in the field that we have. So geopolymer concrete generally is a sustainable concrete, we call it, is a mixture of aluminum silicate source, such as fly ash, slag, or metakaolin, mixed with an activating solution. I call this material as lazy material. So usually we need to have an activating solution to help the reaction started. So we use an activating solution. The most common activating solution is a mixture of sodium silicate, sodium hydroxide, and with water, if we need to have a higher water cement ratio, and mix it with fine and coarse aggregate. There is a lot of, and also we have to have external heat, usually 70 Celsius, which is 154 Fahrenheit, to help to develop and start the reaction of the external heat. Should be between 24 hours and 24 hours to 48 hours. There's several research have been done to investigate the properties, or mechanical and the durability properties of this concrete, and there's very promising result have been achieved. However, still, because it's still a new concrete, there is a lot of things that we could modify to make it better. So my first case study was focusing because this concrete is going to be needed to have external heat. So we're going to have the main only application is precast testing, because we could provide external heat. So my main focus was on the compressive strength. If we improve the compressive strength, we will reduce the need for more volume. So we reduce the size of the column or the beams. So I compare between this is the concrete that I got. This is the with most common activating solution, which is mixture of sodium silicate, sodium hydroxide. We got around 60 megapascal, which is around up to 9,000 psi. However, when I changed to my alternative activating solution, which is mixture of silica fume and sodium hydroxide, we improved the compressive strength by more than 50%. So we increased it up to 116 megapascal, which is around 16,000 psi. And keep in mind, this one subjected to external heat for 24 hours with 70 Celsius, which is 154. And we found that also, I believe this concrete can reach even up to 18 to 22 with fine sand. I just use coarse and fine aggregate. I believe if I remove the sand, I reduce the water cement ratio, I even can move up the compressive strength up to even 150. So then I wanted to see effect of the fly ash source. So we have two different sources, watery station and Blue Sea Creek. And you can see here, the fly ash can really play a dominant role on the compressive strength of the geopolymer concrete, especially fly ash geopolymer concrete, made with the most common activating solution, which is mixture of sodium silicate, sodium hydroxide. I wanted also to see the effect of the same fly ash source on with the alternative activating solution. And you can see here also we have a really big impact due to the change of the source of the fly ash. we did some extra study on to see why we have this such effect. We found out the water station fly ash has a finer particle size distribution. It means that more surface area ready for the reaction. Then I wanted to see the effect of the curing. So generally, when we do this concrete, I mix the activating solution a day ahead, and then we mix it with the dry material, which is fly ash, sand, and aggregate, and we keep it in the mold for 28 days. And we subject it to 24 hours external heat with 70 Celsius, 154 Fahrenheit. And you can see here, the result same what we got is 116, which is 16,000 PSI. However, I wanted to see the effect. How about if we remove the mold after we finish the curing, which is after 24 hours? And you can see here there is no any effect. And also here we didn't use any water for curing or water with lime. So it also has a good advantage that we don't need to waste water to keep the curing going. It's just within, after we subject it to external heat, after 24 hours we will be good to go. And I believe this concrete is good also, especially without the need for mold. Good for a precast or a pre-stress application because we don't need to cure it, and also we can use the form after 24 hours because we reached out to very good compressive strength and we don't need also any curing. Then if I want to use this concrete in many different applications, specifically for example pavement or fly ash, pavement or sidewalk, we need to find a solution for the need for external heat. I need to remove it. So I wanted to see, how about if I remove the external heat? You can see here the same concrete. I just didn't use external heat for 24 hours, and the compressive strength is really reduced drastically from around 80 at one day up to really low, there is no compressive strength. And at 28 days, you can see here is around 30 megapascal, which is around 5,000, around 4,000 psi. But the early compressive strength is not really good, so it's not really useful. So we need to have a solution for that. So then I wanted to see, how about if I reduce the external heat? How about reduce it from 70 Celsius up to 45, which is 120 Fahrenheit, or up to 35 and up to 25. And you can see here the compressive strength, once I reduce the external heat, the compressive strength also reduced due to that. So then I wanted to see also the effect of the sodium hydroxide concentration. How about if we reduce the sodium hydroxide concentration? The sodium hydroxide has a high consumption, energy consumption, and also is expensive. So I wanted to see how about if we reduce it, and you can see here, once I reduce it, the compressive strength really reduced drastically. So I found out there is two main things in this compressive strength, which is the external heat, the concentration of the sodium hydroxide. So I introduce using Portland cement as a partial replacement. So I use 5%, 10%, and 15%. I just replace the fly ash by 5% of Portland cement, 10% or 15%. And you can see here we improve, and this is without any external heat. And you can see here the early compressive strength was really improved, and the final compressive strength without any external heat was more than 60 megapascal, which is around 9,000 psi, and has really good. And the reason why I choose Portland cement, I think, because first of all, Portland cement is available in the market, so it's easy to get. And second thing, Portland cement, when react, can provide us with the heat. And this heat can be really helpful in the geopolymer concrete. And also, the reaction of the Portland cement will produce CSH plus also CH, which is calcium hydroxide. And we can see here, when we have higher alkaline concentration, the compressive strength is going to be increased. So that has a really two advantage. So our hypothesis why we are having really good improvement without really needing for the external heat, we believe that in the presence of the Portland cement, the expelled water, usually the water gonna be resulted out of the geopolymerization process. And this water, if it hasn't been utilized, is going to have, going to evaporate gradually and going to leave micro cracks. So that's why having in the presence of the Portland cement, this water, expelled water, going to be utilized to make CH, which is CSH, which is good, and also CH, which is calcium hydroxide, which is going to react with the available unreacted fly ash particles. So then I wanted to see the effect of the fly ash source. As you can see in the first case study, the fly ash source can really affect on the consistent terrain. So I wanted to see how about if I change it again to another one. So I will compare the watery versus McMaken fly ash source. And you can see also there is also slight effect on the consistent terrain due to changing the fly ash source. And also I wanted to see the effect of the particle size distribution for the same fly ash. And you can see here, once I make the smaller particle size distribution, smaller particle size, the constant trend is increased from 20 megapascal, which is around 3,000 psi, up to more than 60 megapascal, which is around 9,000 psi, just by using finer particle size distribution. So that's also an advantage for us if we are interested in changing the compressive strength or even durability properties. I tested them. I found it really has a low durability, low permeability access due to using finer fly ash. And I think this you can control it by either changing the source or also by changing the particle size distribution. And here we did some XRF result. And also you can see here with 15 has a really very small particle size distribution in comparison with others. Then, based on my experience with this type of concrete, I found that it really has, not really short, but let's say averagely short initial and final setting time. So, this, the general one without using any modification, the time is going to be between 20 minutes to 30 minutes. And I believe if we need to use this in the pavement application or sidewalk or even in the slab on grade, we need to find solution for the initial final setting time. We need to have time to transport it from the ready mix plant to the main to the site. So I introduce sugar, the normal sugar that we use it in our food. And I call it my sweet concrete. And then you can see here, I just add 3, 6%, and 9% of just sugar. And you can see here the initial final set time moved from around 20 to 30 minutes up to, with just 6%, I make it 300 minutes. So it's really good. So I wanted to see how about the effect of the sugar, adding sugar on the mechanical properties, such as compressive strength. And you can see here there is no really main effect on the compressive strength. And that's make me believe the adding sugar didn't affect on the chemical reaction. However, its effect on the physical solution. And here is our hypothesis why we have this improvement, especially in the extension of the initial and final time setting. We believe that adding sugar increases the viscosity, and viscosity gonna really make it hard for the particles to move from side to side. So the particles or the ions make it really taking longer time to move from side to side to make the reaction, which is leading to the delay in the reaction. So before I end with the conclusion, I wanted to also mention another case study, which is the 5th case study. Unfortunately, I don't have the drawings, but I will just explain it briefly. So in one of our Terracon offices in the East Coast, we have a mixed design, use sustainable concrete. The compressive strength, the design compressive strength was 7,500. However, we bore it on the slab on grade, and we found out usually when we bore it, we will make some cylinders, and we transport them the second day after 24 hours to the lab to cure them and test them at 28 days or 7 days based on the client request. And also we left some sample to be cured in the field. We found out any sample that's been transported within 24 hours has a lower compressive strength than what we expecting. We were expecting 7,500. However, anyone we transported within 24 hours, we found it has a lower compressive strength. It's 5,000, which is failing. However, when we tested the one on the field, we found out anyone with any samples, any concrete sample with field cured, we found it meet the requirement. So it was really confusing. So our department manager reached out, and I did study on it, and I found out, I asked him to just keep the sample that's going to be cured in the lab, didn't transport them within 24 hours. I asked him to keep them in the field for 72 hours, which is 3 days. And then they're going to transfer it to the lab to test them after 28 days. And the result was really meeting the requirement. So I believe the reason why we have such a difference between field cured versus if we transport them after 24 hours, and the compressive strength, they believe that because it has a higher slag replacement, more than 50%, this leads to a delay in the initial and final setting time. This means that we cannot transport it after 24 hours because we don't have enough strength, and also the transporting time, the vibration gonna really affect and make micro cracks, leading to the effect on the final compressive strength. So when we waited 72 hours, that means the reaction is slow, but it's progressing. That's make it has enough strength to transport it without any compromising the samples. So with that, the conclusion, we improve the early and final compressive strength by more than 50%, and also we eliminate the need for external heat by using 5 to 10% of Portland cement. And also we found out the fly ash source and particle size distribution play dominant part in the mechanical and durability properties. That's why if we need to control any properties, we can really just use finer fly ash or different source of the fly ash. And also, we significantly delay the initial and final setting time by just using 3% or 6% sugar, and that's going to help us to delay the reaction. With that being said, I'm really thank you for listening, and happy to answer any question you might have.